Your phone is dead. The screen is black. The little blue dot that tells you where you are is gone. Now what? For most of us, this is a moment of panic. We are so used to technology telling us where to go, we trust it completely. But what if that trust is misplaced? What if it all just stopped working? People crossed oceans for thousands of years. They navigated vast, empty deserts. They built empires that spanned continents. They did it all without a single satellite. They did it with their eyes, their hands, and their minds. They read the world around them like a map. A map that was always there, written in the stars, the waves, the wind, and the dirt. The Vikings found North America 500 years before Columbus. The Polynesians settled islands scattered across millions of square miles of the Pacific, an area larger than all the continents combined. They did not do this by accident. They had tricks. They had knowledge. This was not magic. It was a deep practical understanding of the natural world, and a kind of literacy we have almost completely lost. We have outsourced our sense of direction to a machine. And in doing so, we have forgotten how to read the language of the planet. Are we smarter for it or just more fragile? Let's look back at some of the ways our ancestors found their way. These are not just historical curiosities. They are a reminder of a different way of seeing the world. A way of being present and aware, not just following a digital line. Number 15, can a simple stick tell you where to go? Yes. A stick in the ground can be a remarkably accurate compass. This is one of the oldest and most fundamental ways to find direction. It requires only two things, the sun and a shadow. People have been using this method since before recorded history. It's simple, but it works. Here is the basic idea. You take a stick, maybe a meter long. You push it vertically into flat, clear ground. Now you watch its shadow. The sun moves across the sky. So the shadow moves too. In the morning, the shadow will be long and will point somewhere west. As the sun climbs higher, the shadow gets shorter. At noon, the shadow is at its shortest. Then, as the sun begins to set, the shadow gets longer again, pointing east. To find east and west, you use a marker. A small stone works perfectly. Go out in the morning, a few hours before noon. Mark the very tip of the stick's shadow with your stone. Now you wait. You have to be patient. You go do something else for a few hours. Come back in the afternoon. The shadow will have moved. It will be on the other side of the stick. Wait for the shadow to become the exact same length as it was when you made your first mark. Mark the tip of this new shadow with a second stone. Now you have 2 points on the ground. Draw a straight line between them. That line runs almost perfectly east to west. Your first mark is west. Your second mark is east. If you stand with the west mark on your left and the east mark on your right, you are facing north. It's that simple. This is called the shadow tip method. There is an even simpler way if you have more time. Just watch the shadow as it moves around midday. The shadow is shortest when the sun is at its highest point in the sky. This moment is called solar noon. In the northern hemisphere, the shortest shadow of the day points directly to true north. Not magnetic north, which a compass shows, but true geographic north. In the southern hemisphere, it points to true south. So if you can identify the shortest shadow, you have found a perfect north-south line. Who used this? Everyone. Ancient Egyptians used giant obelisks, which were essentially massive shadow sticks, to track the sun and mark ceremonial times. Travelers on the Silk Road, crossing the vast and featureless deserts of Central Asia, would have relied on this to keep their caravans moving in the right direction. But perhaps the most interesting users were the Vikings. We know from Norse sagas that they were expert navigators. They sailed the brutal North Atlantic in open longships. They needed reliable ways to find their way when out of sight of land. Researchers have found an object in Greenland called the Unartok disk. It's a small wooden disk dating to around 1000 AD. It has lines carved into it. Some archaeologists, like Christian Keller of the University of Oslo, believe it was a type of portable sun compass. A central pin would cast a shadow onto the lines. By keeping the shadow on a specific line, a Viking navigator could hold a steady course. This was a sophisticated version of the simple stick in the ground. It allowed them to find direction even when the sun was not at its highest point. The science behind this is just the rotation of the Earth. The sun appears to move in a predictable arc across the sky. The shadow cast by a vertical object traces a corresponding arc on the ground. By marking points on that arc, we are essentially using the Earth itself as a giant clock and compass. It is a system of beautiful, simple geometry, a 2013 study published in the journal Proceedings of the Royal Society. They successfully tested the viability of Viking sunstones and sun compasses, showing they could determine direction with a surprising degree of accuracy, even on partially cloudy days. But this knowledge is fragile. We have forgotten it. We rely on a phone that can run out of battery. The Vikings relied on a stick and a shadow. One system is complex and brittle. The other is simple and robust. It works as long as the sun shines and the earth turns. Still, we have questions. How accurate could a navigator be on the deck of a ship that was constantly rolling and pitching? Was the shadow stick a tool for when they made landfall, to reorient themselves, rather than a primary tool at sea? The Ulunartok disk seems designed for a ship, but how widespread was this technology? Was it a secret known only to a few master navigators, or was it common knowledge among all Viking sailors? And how did they account for the changing seasons, which alter the sun's path across the sky and the length of the shadows it casts? Number 14, is there one star that never moves? There is, or at least, it moves so little that it seems to be fixed in the sky. For anyone in the northern hemisphere, this star has been the single most important anchor in the night sky for centuries. We call it Polaris, the North Star. Finding it is the first lesson of celestial navigation. First, you find the Big Dipper. It is a large, bright, and easily recognizable group of 7 stars. It looks like a pot or a ladle. The 2 stars at the end of the pot part opposite the handle are called the pointer stars. Their names are Merak and Dubhe. If you imagine a line running through these 2 stars and extend it up out of the pot, it points almost directly to Polaris. The distance is about 5 times the distance between the 2 pointer stars themselves. Polaris is not the brightest star in the sky. It is actually the 48th brightest. But it is special because of where it is. It sits almost directly above the Earth's North Pole. As the Earth spins on its axis, all the other stars appear to rotate in great circles around Polaris. But Polaris stays put. It is a fixed point, a celestial pin in the fabric of the night. If you are standing at the North Pole, Polaris is directly overhead. If you are at the equator, it is right on the horizon. The angle of Polaris above the horizon is equal to your latitude. This was a revolutionary discovery for sailors. With a simple tool like an astrolabe or a quadrant, a navigator could measure this angle. This told them how far north or south they were. It was the first reliable way to determine latitude at sea. Christopher Columbus relied heavily on Polaris during his voyages. His journals from 1492 are filled with mentions of taking readings of the North Star. He used it to calm his crew, who feared they were sailing off the edge of the world. He showed them how the star's height changed as they sailed west, proving they were traveling along a curve, not a flat line. But even Columbus made mistakes. At one point, his measurements were so off that he concluded the Earth was shaped like a pear, not a perfect sphere. This shows that even with a fixed point, human error is always a factor. The person who really codified the use of Polaris for navigation was the Portuguese explorer and cosmographer Pedro Nunes. In his 1537 Tratado da Esfera, he laid out the mathematical principles for navigating by the stars. He understood that Polaris is not perfectly aligned with the celestial pole. It makes a tiny circle around it. Nunes developed methods to correct for this small error, making latitude calculations even more precise. But there is a catch. The Earth wobbles. It's a very slow wobble called axial precession, taking about 26,000 years to complete one cycle. This means the North Star changes over time. When the Egyptians built the pyramids around 2500 BC, the North Star was a different star called Thuban, in the constellation Draco. For the ancient Greeks, there was no single bright star near the pole. Polaris only became the reliable North Star during the late Roman era and will continue to be for another 1,000 years or so. In about 12,000 years, the bright star Vega will be the North Star. Our constant in the sky is not so constant after all. It is just constant enough for our own short history. Using Polaris was a core skill for every sailor, explorer, and traveler in the northern hemisphere for well over 1,000 years. It was the anchor that made the age of discovery possible. Before GPS, it was the closest thing we had to a satellite in the sky. It was a single, reliable point in a sea of movement and uncertainty. But what did sailors do on cloudy nights? A week of bad weather could leave a ship completely blind, relying on guesswork. How did early navigators, before the invention of precise angle measuring tools, estimate latitude from the star's height? Was it just based on handspans against the horizon? And how much did the average person, a simple farmer or soldier, know about the North Star? Or was this specialized knowledge reserved for a select few? Of number 13, what if the North Star disappears? If you travel south of the equator, Polaris sinks below the northern horizon. It is gone. Suddenly, the most reliable guide in the sky is useless. For explorers venturing into the southern hemisphere, this was a terrifying prospect. They were sailing into a sky they did not recognize. There was no bright, convenient star sitting directly over the South Pole. The entire system of navigation they had relied upon was broken. They had to learn a new sky. They had to find new signposts. In the south, the most important constellation for finding direction is the Southern Cross, or Crux. It is a small but very bright and distinct constellation made of 4 main stars. It looks like a kite. Unlike the Big Dipper pointing to Polaris, the Southern Cross does not point directly to the South Celestial Pole, but it can be used to find it. There are 2 ways. The first method involves the cross itself. Imagine a line extending from the top star of the cross through the bottom star. Extend that line out about 4.5 times its own length. That point is roughly the South Celestial Pole. The other method involves 2 other bright stars, called the pointers. These are Alpha and Beta Centauri. They are not part of the Southern Cross, but are nearby. Imagine a line between these 2 pointers. Find the midpoint of that line. Now draw a perpendicular line from that midpoint out into the dark part of the sky. Where that imaginary line intersects the line from the Southern Cross is the South Celestial Pole. Once you find that spot, you can drop a line straight down to the horizon to find true south. This sounds complicated. It is. It is much less direct than finding Polaris. It required more skill and more judgment. Early European explorers struggled with it. When Ferdinand Magellan's expedition circumnavigated the globe between 1519 and 1522, the chronicler Antonio Pigafetta wrote extensively about the new stars they were seeing. He described the Southern Cross in detail. For his crew, learning to use these new constellations was a matter of life and death. Long before the Europeans, however, other cultures were masters of the southern sky. In Polynesian wayfinders, perhaps the greatest navigators in human history, did not rely on a single pole star. They had a much more sophisticated system. They memorized the entire star field. They knew the specific points on the horizon where each major star would rise and set. This is called a star compass. Instead of just north, south, east, and west, their compass might have 32 or more points, each marked by a rising or setting star. A 2011 study by researchers at the Australian National University, looking at the oral traditions of navigators in the Caroline Islands of Micronesia, confirmed the complexity and accuracy of these systems. A master navigator, a Palu, would spend a lifetime learning these star paths. They could hold a course to a tiny, distant island just by keeping their canoe aligned with a specific rising or setting star. When that star rose too high, they would switch to the next one on the path. It was a dynamic, living form of navigation that required immense memory and a deep intimacy with the sky. Other constellations were also used for direction in both hemispheres. Orion, the hunter, is a great example. It straddles the celestial equator, so it is visible from almost everywhere on Earth. Orion's belt, the 3 bright stars in a row, rises in the east and sets in the west. No matter where you are, it follows this path. For a traveler on land or at sea, watching the rise and set of Orion's belt provides a reliable east-west line. So when the North Star disappeared, navigators were not lost. They just had to use a different set of tools. They had to read more of the sky, not just one special star. It forced them to develop a more holistic and flexible understanding of the cosmos. But so much of this knowledge was passed down orally. How much have we lost? We have the journals of Europeans, but what about the star maps that existed only in the minds of Polynesian masters? Did different cultures in the southern hemisphere, from Aboriginal Australians to the Sand people of the Kalahari, develop entirely different systems for reading the southern sky that we now know nothing about? And could these complex mental star maps ever be fully recreated, or are they gone forever once the last practitioner is gone? Number 12, does the moon lie? The moon can be a guide, but it is a tricky one. Unlike the sun or Polaris, the moon is constantly changing. It changes its phase, it changes its position in the sky, it rises and sets at different times each day. Using the moon for navigation is more complex than using the sun, but it can be done. The simplest way to use the moon is just like the sun. It rises in the east and sets in the west. If you see a crescent moon rising, you know that direction is roughly east. If you see it setting, that is roughly west. This gives you a general orientation. But it is not precise. To get more accurate, you have to understand the moon's phases. Here is a simple trick that works in the northern hemisphere. If the moon rises before sunset, its illuminated side will be on the west. If it rises after midnight, its illuminated side will be on the east. Think of it this way. The sun lights up the moon, so the bright side of the moon is always pointing towards the sun's position, whether the sun is above or below the horizon. There is another method using the horns of a crescent moon. Imagine a line connecting the tips of the crescent. Extend that line down to the horizon. In the northern hemisphere, that point on the horizon will be roughly south. In the southern hemisphere, it will be north. This is because the sun, moon, and planets all travel along a similar path in the sky, known as the ecliptic. This method essentially points you towards the pole that is tilted away from the sun. These are rules of thumb. They can get you out of a bind, but they are not for precise, long-distance navigation. The moon's path across the sky changes with the seasons and over an 18.6-year cycle called the lunar nodal precession. A medieval navigator would not have known the complex orbital mechanics, but they would have noticed the patterns through long observation. The real power of the moon for medieval navigators was not in finding direction, but in understanding tides. For anyone sailing near a coast, tides are critical. They create strong currents that can pull a ship off course or onto rocks. A full moon or a new moon creates the strongest tides, called spring tides. A quarter moon creates the weakest tides, called neap tides. An experienced coastal pilot would know the rhythm of the tides in their local waters. They would know that high tide occurs at a specific interval after the moon passes its highest point in Thesky. This knowledge was essential for entering and leaving shallow harbors. The English monk Bede, writing in the 8th century in his work The Reckoning of Time, was one of the first to systematically link the tides to the phases of the moon. He observed that high tide followed the moon's position by a consistent amount of time for any given port. This understanding was a major breakthrough. It turned the confusing and dangerous tides into a predictable, usable pattern. A sailor who understood Bede's work could plan their journey to use the tidal currents to their advantage, saving time and effort. The moon was also a clock. Before mechanical clocks were common or reliable, the moon was one of the ways people told time at night. Just as the sun's position tells the time of day, the moon's position, combined with its phase, can give a rough estimate of the time of night. For a watchman on a ship's deck, tracking the moon's progress across the sky was a way to measure out the long hours of their watch. So the moon does not lie, but it speaks a more complicated language than the sun. It is a guide of cycles and rhythms, of tides and time. It requires a deeper level of observation. It is not a simple fixed point, but a dynamic partner in the sky. But we still wonder how much of this lunar knowledge was written down, and how much was just sailor's lore passed from master to apprentice. Did navigators on long ocean voyages, like the Vikings, have a system for using the moon's position to estimate longitude, a problem that would not be officially solved until the 18th century? And were there lunar myths and stories that contained hidden navigational clues, which now just seem like folklore to us? Number 11. Can you read the ocean's mind? Out on the open ocean, the sky can be covered with clouds for days. The sun, moon, and stars all disappear. In these moments, a navigator needs another map. That map is the surface of the ocean itself. An experienced mariner can read the waves. They can feel the direction of the sea. There are two kinds of waves. There are wind-driven waves, which are choppy, irregular, and change direction whenever the wind changes. Then there is the swell. The swell is different. It is a pattern of long, smooth, rolling waves. These waves are not created by the local wind. They are the ghosts of distant storms. A storm hundreds or even thousands of miles away creates huge waves. As these waves travel across the ocean, they lose their choppiness and become a steady, predictable rhythm. This swell can travel for enormous distances, and it holds its direction. The prevailing winds in a region like the trade winds create a constant underlying swell. Is a navigator who knows the direction of this prevailing swell has a natural compass. Even when the sky is gray and the local wind is blowing from a different direction, they can feel the deep, steady push of the swell against the hull of their boat. The Polynesians were the absolute masters of this. They sailed between tiny islands separated by vast stretches of open water. Finding an island that is only a few miles wide from hundreds of miles away is an incredible feat. They use the swell to do it. As a swell passes an island, it refracts and reflects. The pattern of the waves changes. A navigator in their canoe could feel these subtle changes. They could feel the shadow of an island in the waves long before they could see it. They could feel how the waves bent around the land. This told them an island was near, and in which direction. To teach this skill, they created incredible objects called stick charts. These are not maps in our sense of the word. They do not show land masses. They show the ocean. They were made of thin strips of wood tied together. Curved sticks showed the patterns of swells as they bent around islands. Small shells tied to the sticks represented the islands themselves. A stick chart was a mnemonic device, a way for a young navigator to memorize the wave patterns of a specific part of the ocean. The Marshall Islanders, in particular, were famous for their charts, known as Meadow and Rebelib. The Norwegian explorer Thor Heyerdahl brought attention to these ancient techniques with his 1947 Kon-Tiki expedition. He sailed a simple balsa wood raft from Peru to Polynesia to show that such voyages were possible. While many of his theories about the settlement of the Pacific have been disputed by modern historians and geneticists, his journey was a powerful demonstration of how people could survive and navigate the open ocean with only natural methods. He and his crew learned to read the swell as a primary source of direction. This is a skill that is almost entirely learned by feel. It is about being in tune with the boat and the water. A modern sailor, accustomed to looking at a screen, might not even notice the underlying swell. But for a medieval navigator, this was a constant stream of information. They would lie down on the deck of the ship to better feel the motion. Some Polynesian navigators were said to be able to feel the subtle slap of a reflected wave against the hull from a specific direction. This kind of knowledge, sometimes called wave piloting, is a deep embodied skill. It is not something you can easily learn from a book. It requires years of practice and a profound connection to the ocean environment. It is a reminder that navigation is not just about seeing, it is also about feeling. But how sensitive were they really? Could a navigator on a large, heavy Viking longship feel the subtle wave patterns in the same way a Polynesian in a small outrigger canoe could? The stick charts are abstract representations. How were they actually used in a practical sense during a voyage? Were they consulted like a modern map, or were they just for training on land? And is there a limit to this skill? Could it be used to find a completely unknown island, or only for traveling between known points? Number 10, are clouds just water vapor, or are they maps? From the deck of a ship in the middle of the ocean, the world can feel like an endless expanse of blue. But even there, the sky holds clues about what lies beyond the horizon. Clouds are not just random puffs of white. Their shape, color, and behavior can signal the presence of land. The most important type of cloud for a navigator is the stationary cloud. On a day with a steady wind, you will see clouds moving across the sky. But if you see one cloud that seems to be stuck in place, that is a very important sign. Islands, especially mountainous ones, create their own weather. Warm, moist air from the ocean is forced upward as it passes over the land. As this air rises, it cools, and the moisture condenses to form a cloud. This cloud will hang over the island, even as other clouds are blown past by the wind. For a sailor scanning the horizon, this stationary cloud is a beacon. It is a signpost that says land is here, long before the land itself is visible. The color of clouds can also be a clue. The underside of a cloud over a green, jungle-covered island might have a faint greenish tint. This is because of the light reflecting up from the vegetation. Similarly, a cloud over a large, shallow lagoon might have a pale, turquoise hue reflected from the water below. A cloud over a white sand desert or a snowy ice cap might appear unusually bright on its underside. These are subtle clues. They require a trained eye and perfect weather conditions. But for a desperate crew searching for a place to make landfall, any clue is a good one. This type of observation was crucial for the settlement of the Pacific. A study published in the Proceedings of the National Academy of Sciences in 2014 used computer simulations to model Polynesian voyages. The study, led by Alvaro Montenegro, found that including these subtle environmental cues, like stationary clouds, dramatically increased the success rate of finding small, remote islands. It turned voyages of pure chance into voyages of calculated probability. Birds are another part of the sky map. Certain types of seabirds, like terns and boobies, fly out to sea in the morning to feed and return to their nests on land in the evening. A navigator who sees a flock of these birds flying purposefully in one direction at dusk can be fairly certain they are flying towards land. By following them, they might find their way to an island. The direction, species, and behavior of the birds all provide information. A single bird flying high might just be lost. A large flock low to the water is probably heading home. Even the behavior of the air itself changes near land. The smell of the land is a real phenomenon. After a rain, the smell of wet earth and plants can carry for miles out to sea. Sailors also notice changes in the wind. A steady ocean breeze might become gusty and unpredictable near a large landmass as the terrain disrupts the flow of air. These are not precise navigational tools. They will not give you a latitude or a longitude. But they are tools of discovery. They are the clues that tell a navigator to pay attention, to change course, to look more closely at the horizon. They are about reading the environment as a whole system where the sky, the sea, and the land are all interconnected. A cloud is not just a cloud, it is a reflection of the world beneath it. But we have to ask, how reliable were these signs? A cloud could be just a slow-moving cloud, not a sign of land, leading a ship on a fruitless chase. Following a flock of birds could lead to a barren rock with no fresh water. How did navigators learn to distinguish between a true sign and a false one? Was it just trial and error, a brutal process where the ones who guessed wrong simply did not return? And how far out to sea could these effects, like the color of a cloud, actually be seen with the naked eye? Number 9, could a flock of birds be your best guide? Yes. For thousands of years, birds have been one of humanity's most reliable guides. Long before we understood the science of magnetic fields or orbital mechanics, we understood a simpler truth. Birds know where they are going, and if you follow them, you might get there too. This is not just about following land-based birds back to their nests in the evening. This is about using the great seasonal migrations of birds as a highway across the world. Every spring, billions of birds fly north. Every autumn, they fly south. They follow predictable routes called flyways. These flyways often cross vast stretches of open water or featureless desert. An ancient traveler who knew these routes could use the birds as a living compass. The most famous example of this comes from the Viking sagas. The story of the settlement of Iceland is told in the Landnámabók, or the Book of Settlements. It tells of a Norwegian navigator named Hrafna Floki Vilgerdarson, or Raven Floki. Around the year 868, he set out to find a new land that had been reported in the north. He took 3 ravens with him. After sailing for some time, he released the first raven. It flew up, circled, and then headed straight back to Norway. Floki knew he was still closer to home than to his destination. He sailed on. He released the second raven. It circled for a while and then landed back on the ship. This told him he was far from any land. He sailed on again. Finally, he released the third raven. It flew up and then headed purposefully northwest. Floki followed it. The raven led him directly to the coast of Iceland. Is this story literally true? We do not know. The sagas were written down hundreds of years after the events they describe. But the principle is sound. Ravens are intelligent birds. They prefer to be on land. If released at sea, their instinct would be to fly towards the nearest landmass. A smart navigator could use this instinct to their advantage. It was a kind of biological sonar. This technique was not unique to the Vikings. Polynesian navigators also paid close attention to migratory birds. They knew the flight paths of birds like the Pacific golden plover and the long-tailed cuckoo. These birds migrate between Alaska and islands like Hawaii or Tahiti. Seeing a flock of these birds during the migration season gave a navigator a clear directional line to follow. It was not just a general direction, it was a specific path leading from one known place to another. In a 2015 book, The Wayfinders, anthropologist Wade Davis details how this knowledge is part of a much larger system of observation. The navigators knew not just the direction of the birds, but also the time of year they would appear, their altitude, and their flock size. All of this was data. It was fed into a complex mental calculation about their own position and the location of their target. Even on land, birds were guides. In the Kalahari Desert, the San people have a remarkable relationship with a bird called the honey guide. The bird loves to eat beeswax and bee larvae, but it cannot break into the hive itself. Humans love honey, but have trouble finding the hives, so they work together. A honey guide will find a person and chatter at them, leading them through the bush. The person follows, sometimes for miles. The bird leads them directly to a bee's nest. The person smokes out the bees, takes the honey, and leaves the wax and grubs for the bird. A 2016 study in the journal Science, led by Dr. Claire Spottiswoode, confirmed that this is a true two-way communication between species. For the sand, following a bird is not a trick. It is a partnership. This reliance on birds shows a different relationship with the natural world. It is not about imposing a human system like a grid of latitude and longitude onto the planet. It is about observing the existing systems of the planet and fitting into them. The birds are already traveling. The flyways are already there. The clever navigator is the one who learns to see these patterns and use them. But how did a sailor in the middle of the ocean distinguish a migrating flock from a group of birds that was simply lost? The sky is a big place. How often would a ship and a flock of migrating birds actually cross paths at the right moment? And what about the story of Raven Floki? Was carrying birds for navigation a common practice, or was this a unique, legendary tale? We have so few archaeological records to confirm these practices. Number 8. Did ancient mariners follow whales? The ocean is not empty. It is filled with life, and much of that life is on the move. Just like birds, many species of whales undertake massive annual migrations. They travel from cold, food-rich feeding grounds in the polar regions to warm, safe breeding grounds in the tropics. They travel in predictable routes year after year. For an ancient mariner, these whale roads could have been another set of signposts in the vast ocean. The gray whale is a perfect example. Every year, they travel up to 12,000 miles round trip. They go from the Arctic waters of the Bering and Chukchi Seas down to the warm lagoons of Baja California in Mexico. This is one of the longest migrations of any mammal on Earth, and they stick to the coast. A sailor moving along the Pacific coast of North America in the right season would have seen a steady stream of gray whales moving north or south. This procession would not just confirm their general direction of travel. It would also tell them something about the time of year. In the Atlantic, the humpback whale makes similar journeys. They feed in the cold waters off Greenland, Iceland, and Norway in the summer. In the winter, they travel south to the Caribbean and the waters off West Africa to breed. For a Viking ship sailing from Norway to Iceland, or a Portuguese caravel exploring the coast of Africa, encountering a pod of humpbacks would have been a common event. Did they actively follow them? It is hard to say for certain. We do not have written records from medieval sailors saying, "We followed the whales to get to our destination." But it is highly likely that this knowledge was part of the general lore of the sea. An experienced captain would know the seasons and routes of the whales in their home waters. This information would be another layer in their mental map of the ocean. It would tell them they were on the right track and in the right season. The connection between humans and marine mammals is ancient. The maritime historian Brian Fagan, in his book The Attacking Ocean, describes how coastal peoples have always lived in close relationship with the sea's creatures. They knew their habits intimately because their lives depended on it. For them, a whale was not just a creature. It was an event, it was a sign. There is also a more practical reason to pay attention to whales. Whales need to eat. They tend to congregate in areas where there is a lot of food. These are often areas where cold, deep water rises to the surface, a phenomenon called upwelling. These upwelling zones are rich in nutrients and support a huge amount of marine life, from krill and small fish all the way up the food chain. These areas are often found near coastlines and over underwater mountains, or seamounts. A concentration of feeding whales could therefore be an indirect sign of nearby land or a significant change in the seabed, both of which are crucial pieces of information for a navigator. This is another example of reading the entire environment. A whale is not just a whale. It is an indicator of a whole ecosystem. Its presence tells a story about the water temperature, the food supply, and the time of year. A medieval sailor would not have understood the biology of upwelling, but they would have understood the simple, practical connection. Where there are many whales, there is often land or shallow water nearby. This is a form of navigation that is based on life. It is not about abstract geometry or dead reckoning. It is about seeing the ocean as a living, breathing place full of patterns and habits. The animals are not just scenery, they are part of the map. But how consistent were these migrations? Did whales ever change their routes, leading sailors astray? Without modern tracking, it's impossible to know how predictable their paths were 1,000 years ago. And how would a sailor on a slow-moving sailing ship follow a whale, which can travel much faster? Was it more about seeing them as a reassuring sign that you were in the right corridor of the ocean rather than following a specific individual? The evidence for this technique is more circumstantial than for others. It is a logical inference, but what direct proof do we actually have? Number 7. What does land smell like from the sea? You can smell land long before you can see it. For a sailor who has been at sea for weeks, surrounded by the clean, salty smell of the open ocean, the first scent of land is an unmistakable and powerful signal. It is the smell of safety, of fresh water, of an end to the journey. This is not a romantic notion. It is a scientific fact. The smell of the land is made up of several things. One of the most powerful components is a compound called geosmin. This is the chemical that gives soil its rich, earthy smell, especially after it rains. Geosmin is produced by bacteria in the soil. It is incredibly potent. The human nose is extremely sensitive to it. We can detect it at concentrations as low as a few parts per trillion. A gentle offshore breeze can carry the smell for many miles out to sea. Another component is the smell of plants. Pine forests, eucalyptus groves, or fields of flowering plants all release volatile organic compounds into the air. These scents, carried on the wind, create a unique aromatic signature for a particular coastline. An experienced mariner, familiar with a specific route, might even be able to identify a place by its smell. This smells like the pine barrens of home, they might think, confirming their location. The great explorer Captain James Cook, one of the most meticulous navigators in history, mentioned the smell of land in his journals during his voyages in the 18th century. While charting the coast of New Zealand, he noted the agreeable smell that came off the land, which he attributed to the plants and trees. For Cook, this was another piece of sensory data to add to his charts and observations. This technique is most effective in areas with prevailing onshore or offshore winds. The wind acts as a carrier, bringing the information to the ship. A sailor would pay close attention to the wind's direction. A shift in the wind could suddenly bring the scent of a previously undetected island. Smoke is another powerful olfactory signal. A fire on land, whether a natural forest fire or a campfire from a human settlement, produces a plume of smoke that can be seen and smelled from a great distance. For an explorer arriving on an unknown coast, the smell of wood smoke was a clear sign of human habitation. This could be a sign of danger or an opportunity for trade, but either way, it was vital information. The sounds of land also travel over water. The sound of waves crashing on a reef or a beach can be heard from miles away, especially on a calm night. This was a crucial warning sign. The sound of breaking waves told a navigator to be cautious, that shallow water or hidden dangers were near. The sound of birds, especially large colonies of seabirds on coastal cliffs, could also act as an auditory beacon. This is a form of navigation that uses the most primal of senses. Smell and hearing are deeply connected to memory and emotion. The smell of land was not just an abstract piece of data like a number on a screen. It was a visceral emotional experience. It was the smell of the end of hardship. But this is perhaps the most subjective of all the techniques. How far can a smell really travel over the open ocean? Does the humidity and temperature of the air affect it? And how could a navigator be sure that what they were smelling was land, and not just a mass of floating seaweed or a strange atmospheric condition? Without the ability to scientifically verify these smells, how much of it was just wishful thinking by a homesick crew? Number 6, can water itself tell you where you are? The ocean is not a uniform body of water. It changes its color, its temperature, its clarity, and even its life can tell a story about where you are. Is a navigator who knows how to read the water is reading one of the most detailed pages of the natural map. The color of the water is the first clue. Deep ocean water, far from land, is typically a dark, inky blue. This is because there is little suspended sediment or organic matter. The water is clear, and blue light penetrates the deepest. As a ship approaches a coastline, the water color often changes. It might become greener. This green color is caused by phytoplankton, tiny marine plants that are more abundant in the nutrient-rich waters near land. A shift from deep blue to greenish blue is a sign that the environment is changing, that you are likely moving from deep to shallower water. Near the mouth of a large river, the water can turn brown or yellow. This is due to the silt and sediment carried by the river and dumped into the sea. A sailor seeing a plume of muddy water extending out into the ocean would know that a river mouth was nearby. This was a welcome sight, as it meant a source of fresh water. The journals of early explorers sailing along the coast of South America, for example, frequently mention sailing through the massive freshwater plume of the Amazon River, which can be detected more than 100 miles offshore. Water temperature is another vital sign. Ocean currents are like giant rivers carrying huge volumes of warm or cold water across the globe. The Gulf Stream in the Atlantic is a famous example. It is a current of warm water that flows from the Gulf of Mexico up the east coast of North America and then across to Europe. A medieval sailor crossing the North Atlantic would have noticed a distinct change in water temperature as they entered or left the Gulf Stream. They would not have had a thermometer. They would have simply felt the difference in the water or the air. This temperature shift could help them confirm their position. Benjamin Franklin famously created the first detailed chart of the Gulf Stream in 1770, but sailors had known about and used this warm river in the ocean for centuries before that. Another fascinating clue is bioluminescence. This is the fire in the sea, the light produced by living organisms like plankton. When the water is disturbed by a ship's hull or an oar, these tiny creatures light up, creating a ghostly green or blue glow. The intensity of this bioluminescence can vary. It is often brighter in nutrient-rich coastal waters. But more importantly, the pattern of the glow can reveal things. A school of fish moving under the surface will create a moving cloud of light. The wake of a whale or a dolphin will be a glowing trail. A skilled observer could use these patterns to understand what was happening beneath the surface, and perhaps even identify the deep sound channel where marine life congregates. Reading the water is a subtle art. It is about noticing the small changes that signal a larger shift in the environment. It is about understanding that the ocean is a dynamic, complex place, not a uniform, empty void. But how consistent are these signs? A bloom of phytoplankton could happen in the open ocean, making the water green far from land. A river's plume could be pushed in an unusual direction by strange currents. Could a sailor truly rely on something as variable as the color of the water? And without thermometers, how accurately could they really gauge water temperature? Was it a reliable tool or just another piece of folklore that might occasionally prove useful? Number 5, how do you map a seabed you cannot see? For a sailor, the most dangerous thing is not the open ocean. It is the land. Specifically, it is the unseen land beneath the water reefs, sandbars, and rocks. Running aground could mean the end of a ship and its crew. To navigate safely, especially in unfamiliar coastal waters, a captain needed to know the depth of the water. They needed a way to see the bottom. The tool they used was the sounding lead. This was a simple but incredibly effective device. It was a lead weight, often shaped like a cone or a pyramid, attached to a long rope. The rope was marked at regular intervals with strips of leather or colored cloth. These marks, called marks and deeps, allowed the sailor to measure the depth. The standard markings were codified by the English Navy and are mentioned in texts as early as the 15th century. For example, a leather strip with 2 ends meant 2 fathoms 12 feet. A white rag meant 5 fathoms. A red rag meant 7 fathoms. The process was called heaving the lead. A sailor, called the leadsman, would stand at the bow of the ship. He would swing the lead and toss it forward. As the lead sank, the ship moved forward over it. When the rope went vertical, the lead had hit the bottom. The leadsman would feel for the bottom, note the mark on the rope that was at the water's surface, and call out the depth to the captain. By the mark 5, he might shout, meaning a depth of 5 fathoms. It was a rhythmic, almost ceremonial process, and the calls of the leadsman were a familiar sound on any sailing ship. But the sounding lead could do more than just measure depth. The bottom of the lead weight was hollowed out. This hollow was armed with tallow or wax. When the lead hit the seabed, a sample of the bottom would stick to the tallow. The leadsman would bring the lead up and examine the sample. Was it soft mud? Coarse sand? Small pebbles? Sharp shells? This was crucial information. Why? Because the seabed has a topography, just like the land. Different areas have different types of bottom. A good sea chart would not just show depths. It would also have notations about the nature of the seabed. For example, A chart might say 40 fathoms fine gray sand. A captain sailing in foggy weather, completely lost, could take a sounding. If his lead came up with fine gray sand from a depth of 40 fathoms, he could look at his chart and find the spot that matched that description. It was a way to pinpoint his location. It was a form of underwater cartography. The ancient Greek historian Herodotus, writing in the 5th century BC, describes sailors approaching Egypt taking soundings. They knew that the Nile River deposited vast amounts of mud on the seabed. When their sounding lead came up with mud from a depth of 11 fathoms, they knew they were exactly one day's sail from the coast. This shows that this technique is ancient. It was a fundamental skill for anyone sailing in coastal waters. The sounding lead was a direct physical connection to the unseen world beneath the ship. It provided two critical pieces of data: depth and composition. With this information, a captain could build a mental model of the underwater landscape, navigate safely into a new harbor, or find a good spot to anchor. Sand or mud is good, rock is bad. It was a simple tool that revealed a hidden dimension of the world, but this method only worked in relatively shallow coastal waters, up to about 100 fathoms. In the deep ocean, it was useless. How did this transition in knowledge affect a sailor's mindset as they left the coast? And how accurate were the early charts that recorded this sounding data? Was a notation of rocky bottom on a 200-year-old chart still reliable, or could the seabed have shifted? And how did the leadsman get an accurate vertical reading from the deck of a ship that was being tossed by waves? Number 4, were medieval maps just fancy drawings? When we think of old maps, we often picture monsters in the sea and wildly inaccurate coastlines. Some medieval maps were like this. They were more about theology than geography. They might show Jerusalem at the center of the world, with the 3 known continents arranged symmetrically around it. These maps, called Mappa Mundi, were not meant for navigation. They were illustrations of a worldview. But at the same time, a completely different kind of map was being developed. It was practical, it was accurate, and it changed the world. This was the Portolan chart. The word Portolan comes from the Italian word portolano, which means pilot book. These charts were made by sailors, for sailors. They appeared in the Mediterranean around the end of the 13th century. The oldest surviving example is the Carte Paysanne, dated to about 1290. A Portolan chart looks very different from a modern map. The most striking feature is the network of lines that crisscross the entire map. These are called rhumb lines. They radiate out from a series of wind roses, or compass roses, arranged in a circle on the chart. These lines are not lines of latitude and longitude, they are lines of constant compass bearing. Here's how they worked. A navigator had a compass. He wanted to sail from Genoa to Tunis. He would find Genoa and Tunis on his chart. He would then find the rhumb line that connected them, or ran parallel to a line connecting them. Let's say that line radiated from the nearest compass rose as south-southwest. The navigator would then simply point his ship south-southwest and sail. As long as he kept his compass needle pointing in that direction, he would eventually reach Tunis. This was a revolutionary system. For the first time, a captain could plot a direct course across open water, out of sight of land, with a reasonable expectation of arriving at their destination. It combined 2 new technologies, the magnetic compass and the Portolan chart. The charts were remarkably accurate for the areas they covered, primarily the Mediterranean and Black Seas. The coastlines were drawn with a precision that was not surpassed until centuries later. This accuracy came from centuries of real-world data, collected by sailors who meticulously measured distances and bearings between ports. One of the most famous examples of a Portolan chart is the Catalan Atlas of 1375, attributed to the cartographer Abraham Crescas. It was a masterpiece of its time, covering a vast area from the Atlantic to China. While the farther reaches were based on Marco Polo's travels and were more speculative, the Mediterranean portion was a working, practical sea chart of incredible detail. The historian Peter Whitfield, in his book The Image of the World, argues that the Portolan chart represents a fundamental shift in human thinking. The old Mappa Mundi showed a world centered on faith and tradition. The Portolan chart showed a world that could be measured, plotted, and navigated by ordinary people. It was a world of straight lines and practical destinations. It was the birth of modern cartography. But the Portolan charts had a hidden flaw. They were drawn as if the world were flat. The rhumb lines were straight. On the relatively small scale of the Mediterranean, this worked well enough. But when explorers like Columbus and Vasco da Gama began making long voyages across the Atlantic and Indian Oceans, the errors started to add up. A straight line on a flat chart is not a straight line on a curved globe. This is the problem of projection, which would not be solved until Gerardus Mercator created his famous Mercator projection in 1569. The Portolan chart was a brilliant tool, but it had its limits. So who were the anonymous sailors who gathered the data for these charts? Their knowledge is the foundation of the charts, but their names are lost to history. How did they measure distance so accurately? Did they use time and estimated speed, or some other method? And why did this incredibly practical and accurate style of map making suddenly appear in the late 13th century? Was it a slow evolution, or was there a sudden breakthrough in knowledge that we are not aware of? Number 3, how did a floating rock change the world? It was a simple observation. A certain type of black metallic rock, if allowed to float freely, would always align itself in the same direction. One end would point north, the other south. This rock was the lodestone, a naturally magnetized piece of the mineral magnetite. The discovery that it could be used to find direction was one of the most important technological breakthroughs in human history. It led to the magnetic compass. The first clear description of a magnetic compass comes from China. In his Dream Pool Essays, written in 1088, the scholar Shen Kuo described how geomancers would rub a needle with a lodestone, magnetizing it. They would then float this needle in a bowl of water, or suspend it from a silk thread. The needle would then point south. The Chinese used this primarily for feng shui, the art of orienting buildings and graves in a harmonious way. But they also began to use it for navigation at sea. Knowledge of the magnetic compass spread slowly westward. It seems to have reached the Arab world and then Europe in the 12th or 13th century. The first European mention of it comes from the English scholar Alexander Neckham in his De Natris Rerum, on the nature of things, written around 1190. He describes sailors using a needle that has been touched by a lodestone to find their way when the stars are hidden. The early compass was a simple affair. It was just a magnetized needle floating in a bowl of water on the ship's deck. It was a fragile and cumbersome tool, but it worked. For the first time, a sailor had a reliable way to know their direction, even on a cloudy day or a starless night. It freed them from total reliance on the sky. Over the next few centuries, the compass evolved. The needle was mounted on a dry pivot, allowing it to swing more freely. It was enclosed in a box to protect it from the wind. A compass card, marked with the 32 points of the wind, was attached to the needle. Now, a helmsman could see not just north, but northeast by east, and all the other points. This dry compass was a much more robust and useful instrument. This innovation is often credited to Italian sailors from the port of Amalfi around the 14th century. The combination of the compass and the Portolan chart was what made the age of discovery possible. A captain could now plot a course on his chart and use his compass to follow it. This is the system of navigation called dead reckoning. You start from a known point. You know your direction from the compass. You estimate your speed. From this, you can calculate or reckon your position. It is prone to errors. A bad speed estimate, a strong ocean current, or a magnetic anomaly could throw your calculations off. Columbus famously had trouble with his compass, noting that it was not pointing to the North Star. He was observing magnetic declination, the difference between true north and magnetic north, a phenomenon that was not well understood at the time. The compass was not a perfect tool, but it was a revolutionary one. It transformed sailing from a coastal hugging, fair weather activity into something that could tackle the open oceans of the world. The historian Daniel Boorstin, in his book, The Discoverers, calls the compass a new sense for humanity. It allowed us to sense a force we cannot see, the Earth's magnetic field, and use it to find our way. That simple floating rock, the lodestone, did not just point north, it pointed to a new future. It pointed towards a truly global world, but the origin of the European compass is still a mystery. Did the idea arrive from China via the Silk Road, or was it an independent invention? The evidence is not clear. How did early sailors deal with magnetic declination? Did they have secret rules of thumb to correct for it long before scientists understood the physics? And what did they think the compass was pointing to? For a long time, many believed there was a giant magnetic mountain at the North Pole that was attracting the needle. The true nature of the Earth's magnetic field remained a deep puzzle. Number 2 was getting lost the safest way to travel. It sounds like a contradiction, but for much of human history, the primary method of sea travel was to hug the coast. It was called coasting or cabotage. It was a slow, careful way of moving from one point to another. The principle was simple. Always keep the land in sight. You sail by day, following the contours of the coast. At night, you pull into a sheltered bay or harbor to anchor. This was not a system for bold explorers crossing open oceans. This was the system for trade, for communication, for the everyday movement of goods and people. The entire Mediterranean world was connected by these coastal routes. The Romans called it Mare Nostrum, our sea, because their ships were constantly moving along its edges, linking Spain to Syria and North Africa to Italy. The main tool for this kind of navigation was not a compass or a star chart. It was a pilot book, or a periplus as the Greeks called it. This was a written set of sailing directions. It was a description of a journey. A typical entry might read, "From the headland of the Sacred Bull, sail east with the mountains on your left for half a day. You will come to the mouth of a river with a small village. Beware the sandbar at the entrance. Fresh water can be found there." This was navigation as storytelling. It was based on landmarks. A uniquely shaped rock, a large tree, a temple on a hill, the color of the cliffs. The navigator had to match what they saw with the description in their pilot book. The most famous surviving example is the Periplus of the Erythraean Sea, a Roman guide to the trade routes of the Red Sea and the Indian Ocean, written in the 1st century AD. It is a practical manual filled with details about ports, anchorages, trade goods, and local peoples. This system required immense local knowledge. A pilot had to know every cove, every reef, every current along their stretch of coast. This knowledge was valuable. It was passed down from master to apprentice. A good pilot was one of the most important people on a ship. This method seems limited. It is slow. You cannot take shortcuts across open water. But it was also safe. If a storm blew in, you could quickly run for the shelter of the coast. If you needed supplies, you were never far from a town or village. If you got lost, you were not truly lost in a vast, empty ocean. You were just unsure of which part of the coast you were on. You could follow it in one direction or the other, and you would eventually find a recognizable landmark. Even the Vikings, famous for their open ocean voyages, used a form of coasting. When they traveled from Norway to Greenland, they did not sail in a straight line. They sailed west to the Shetland Islands, then north to the Faroe Islands, then west to Iceland. Then along the coast of Iceland, and then a final jump across the strait to Greenland. They were hopping from one piece of land to another, minimizing their time in the open, empty sea. Coasting was the backbone of the maritime world for millennia. It is less glamorous than the great voyages of discovery, but it was far more important for the daily life of most people. It built the networks of trade and culture that formed the basis of civilization. It was navigation on a human scale based on seeing and remembering the features of the land. But these pilot books were incredibly valuable. Like, how were they made? Did captains keep secret, private logs that were later compiled into these books? How did they update them when a storm changed a coastline or a landmark was destroyed? And how did a pilot from one region learn the coastline of another? Was there a trade in this kind of information, or was knowledge jealously guarded by local guilds? Number 1 is nature screaming directions at us. Even when we are on land, far from the sea, nature is full of clues. For a traveler in a forest or across a plain, there are signs everywhere that can help determine direction. We just have to learn how to read them. These are not as precise as, a compass or a star, but they can provide a general orientation. One of the most well-known pieces of outdoor lore is that moss grows on the north side of trees in the northern hemisphere. The idea is that the north side of a tree gets the least direct sunlight. It is shadier, cooler, and damper, which is the kind of environment moss prefers. Is this true? Yes, but it is not a perfect rule. In a dense forest, all sides of a tree might be shady. A tree next to a river might be damp all around, but as a general tendency, in an open area, there is often more moss on the north side. You should never trust just one tree, but if you look at 20 trees in an area and you see a consistent pattern of more moss on one side, that side is probably north. The sun has other effects on plants. In the northern hemisphere, the sun is in the southern part of the sky. This means that plants and trees will tend to grow towards the south to get more light. The branches of a tree might be thicker and more numerous on the southern side. The flowers will often open facing south. If you find a sunflower in a field, it will almost certainly be facing the sun in the south. The wind is another powerful force that shapes the landscape. In many parts of the world, there is a prevailing wind that blows consistently from one direction. This wind can act like a sculptor. Trees, especially those in exposed locations, will often be bent over, with their branches flagged in the direction the wind blows. If you know the direction of the prevailing wind in a region, these trees become a compass. In many coastal areas, the trees will all be leaning away from the sea. Even the ground can hold clues. In colder climates, snow will melt faster on the south-facing slopes of hills because they get more direct sunlight. In the morning, you might find that the frost is still on the ground in the shadow of a ridge, while it has melted everywhere else. This shadow line runs east-west. These techniques were the common knowledge of hunters, travelers, soldiers, and anyone who lived and worked outside. The famous Otzi the Iceman, a 5,300-year-old mummy found in the Alps in 1991, was a traveler. The analysis of his body and equipment, detailed in the book Otzi, The Man in the Ice by Conrad Spindler, shows he was well equipped for moving through the high mountains. He would not have had a map or a compass. His navigation would have been based on this deep, intimate knowledge of his local environment, the shape of the peaks, the direction of the wind, the feel of the sun. This is the most fundamental kind of navigation. It is not about tools or technology. It is about awareness. It is about paying attention to the small, subtle patterns of the natural world. It is about seeing the world, not as a passive backdrop, but as an active, information-rich environment. All of these clues taken together can create a reliable mental map that can guide you home. But how much of this natural lore is actually true, and how much is just myth that has been passed down? The moss on the tree rule is a perfect example of a clue that is only sometimes reliable. How did people in the past distinguish between the reliable signs and the unreliable ones? And in a world that is now so shaped by human activity, with our roads, power lines, and uniform forests, have we erased many of these natural clues, making this kind of navigation impossible even for those who know how to do it? Is there a point where the natural map becomes unreadable?